Okay, welcome back. I hope you enjoyed your break. Hopefully there's a few more people in the hallway that would like to come in and partake in this. At this time, we're ready to begin the Downhole Well Site Solution session. Our first speaker for this session is Larry Harms. Larry established Harmsway, LLC in 2016 after a 38-year career with ConocoPhillips. There, he specialized in holistic production optimization. Larry was a leader in the artificial lift network for 10 years and is currently president of the Artificial Lift Research and Development Council. As an SPE author and trainer for industry, Larry has conducted hundreds of training courses in production optimization topics. Larry will present today on unconventional gas lift. Please help me welcome Larry.
Thanks a lot. Oh, nice and loud there. He wasn't ready for me to be talking very loudly here. Appreciate the opportunities to be here. Appreciate the organizers of this event for inviting me. And I do want to talk about unconventional gas lift. And in the year, more than a year since we established this topic, that wasn't the original title I had, but I am glad to take it and run with it, and we're going to talk about two unconventional things, okay? First, we're going to talk about gas lift as it relates to unconventional wells. Why is it a preferred method? And I'm going to be that bold to say not just one to be considered a preferred method. And how are we going to approach that unconventionally? Not exactly like most people approach gas lift, so not the conventional way. So we'll talk about unconventional gas lift in those two ways. I want to point out this little clipping that I literally tore out of my JPT, where Dave Barry, who's a confirmed pump guy, was basically lamenting that as much as it pains him, he says, by the book, gas lift should be the default lift method for shale wells, which is absolutely true, and I'm going to emphasize that today. Again, Dave is a pump guy, and that's what he's saying, because when you look at the criteria for shale wells, they fit a lot better with gas lift than they do with pumps, and I'm going to talk about why that is. And here's Shauna Noonan. I don't know if any of you know Shauna. She was the president of SPE last year, someone who I know who was kind enough to come to the Artificial Lift Research and Development Council gas lift workshop and to give a talk on that. And I just want to highlight what she said as Oxy's chief artificial lift engineer, that they had 20% of their unconventional production on gas lift at that time in 2017, and that all their new drills they're trying to put gas lift on. And also, that's their preferred method in the Permian Basin. And I want to point out, I'm going to talk about high-pressure gas lift. If you look at the mandrels on this little sketch that's in here, that's not how we do things, and I'll be talking about that. But I also want to mention that Oxy has recently had a very successful pilot of 15 wells with the technique that I'm going to be talking about today. So why gas lift? Well, the main reason is because of gas. So these wells that we're drilling, they're kind of oil wells, but they're more like gas wells in a lot of ways. This is some data I pulled from shaleprofile.com that basically is just showing what initial GOR was and then what it went to over 2 years. And I used 2 full years of data with, before COVID. And that shows that for where we are here, about 1,000. This is on average. I know you have ones that are higher. I know you have some that are lower. And then up to 2,500 GOR. And the amazing thing really to me on this one is the Permian, where you start out at 1,800. You think of the Eagle Ford as gassy, starts out a little gassier, but after 2 years, it's gone to a GOR of 5,000. And so these are very gassy wells. And what does that do? Well, with a horizontal well bore, it's nice when we have vertical wells. We can sump that pump, get it below the gas production interval if we want to. Not so in unconventionals. All the gas has to come by that pump. Now, there's a lot of fancy ways that you can use to try to mitigate that, and those are recommended, but the truth is you still have to handle it. It all has to go either up the annulus or it has to go through the pump. And there's something else that has to go through the pump too, right? All the solids have to go through the pump. Pumps don't like solids. Pumps don't like gas. Gas lift does. Okay, beam pumps, I'll just hit kind of the high points, right? We can't get up to the high rates that most of these shale wells will do. Hopefully they will do. And so that's going to adversely affect your economics. That gas interference is a big problem. There's a lot of high failure rates on this with this method. It's a great method. It's most onshore wells. Previously, conventionally, we've always done with beam pump, but we didn't have these kind of dog legs. We didn't have this kind of gas. We didn't have these kind of solids. And then how about ESPs? Well, they can do the high rates, no doubt about it. But there's also a high failure frequency that tends to go with that, high costs, a lot of lost production. And the truth is, if you look at those pump curves, what you're going to see is there's just a limited flexibility there. Only so much you can do. And so we've got huge changes in rates with these wells over time, and one pump just can't handle it. It's going to have to be changed out. Not the same in a water drive reservoir where the rates stay pretty much the same. And a lot of times people can't get down to the producing bottom hole pressures they want to, so they're going with another lift method. So you're talking 2 lift methods, that's going to cost you money. It's hard to distribute corrosion inhibitor. I know corrosion is a substantial problem here. Hard to get it distributed up and down the well bore with an ESP. And again, we have gas interference. I want to talk technical just a little bit. A couple of things, many people have published on this over the years of gas interference and ESPs. Much good work has been done to increase the amount of gas that can go through at least the whole ESP system with gas separators. But if you look at this example, I think I'm being very liberal in it. Dunbar looked at it, tried to establish what limits the amount of gas, where can we determine what that's going to be at as far as pump intake pressure. And when we look at these two cases, what we see is that, let's say after 2 years where we were talking about a 2,500 GOR, and then you go over to the left and you see you're going to be above 1,000 pounds with the amount of pump intake pressure, where you can expect your pump to start losing head. That doesn't mean it won't pump. It just starts losing head. It starts becoming more unstable. And this is with a 90% gas separator efficiency, okay? This is only 10% going through it. Another way to look at it, you can calculate the gas volume fraction going through with 90% separation, and you look at that and then you say, okay, my ESP stage can handle about 25% gas volume fraction. So after we take that 90% out, this says at 25 GOR, you're still at a minimum of 600 or so pounds intake pressure, and that is going to be about where you're going to end up, and you're going to start having problems. So I'm going to illustrate that with a real well here in just a second. It's food for thought. I'm going to put this up with not much commentary. If you don't know this, 50% of the money that's spent in artificial lift in the world is spent on ESPs. And for those, I see a few smirks. And some of us know why. I'll leave it at that. Gas lift, very small. So what do I mean by an unconventional gas lift method? Well, gas lift is a method of lightening a column of fluid, causing it to flow. You got packers and valves. You're injecting your lift gas in the casing, and usually 900 to 1,200 pounds, somewhere in that range, and It dates back to maybe 1945 when a guy named King developed the type of gas lift valve we use right now. High pressure gas lift is different. It both lightens the column, but also ensures you have enough velocity to actually flow those liquids out of the well. So you can get down to low producing bottom hole pressures. You don't need a packer. You can just inject that gas down either the annulus or tubing. You've only got one point, and that's going to be very deep in the well, which is the most efficient place to put the gas. If you've ever done jetting with coiled tubing, it's just like that. Pressures, maybe it's low, maybe it's high, it just depends on what your well needs. We used to have constraints. We couldn't go to 4,000 plus pounds because the casing was low strength and there weren't compressors that existed, but now that there are, so those limitations are gone. So I'm going to submit that the original gas lift is high pressure single point gas lift. They were doing it in 1864 in Pennsylvania with air. So why use this instead of conventional gas lift? Well, really, with conventional gas lift, you're trying to get it 1 point deep in the string to that orifice that's the lowest thing that you can eject through. That's the most efficient thing. That's what you're trying to get to. So in the end, these converge. But high pressure gas lift has the strengths that we can achieve those high flow rates that are comparable to ESPs, and conventional gas lift can't. It's simpler. We're not running as much equipment downhole. Everything you run below the master valve is a risk. It's a risk to you. It's a potential cost to you. Single point gas lift, high pressure gas lift, very easy to optimize. Not a lot going on down there. Don't have to worry about multi-pointing. And when you read that casing pressure, you're basically at a column of gas. If there's a little bit of friction, you're basically got a window. You've got a window to what is happening at the bottom of that tubing, which you can set deep in the well. For here, I think it's really important. You can distribute that corrosion inhibitor really well. Just atomize it, put it into whichever side you're putting the gas into. It's going to go all the way down to the deepest point in the well. You can run it to the heel if you want, but the deepest point of the well that you want to run that tubing to, and it's distributed across that whole interval, which really helps with corrosion. So, what kind of setup do you need? Well, I've already talked about in the well. It's really simple. You just need a string of tubing. Okay? On the surface, you need some more kit. You've got basically a gas lift setup, but you're going to add a booster, which is shown here in yellow, to get that gas up to high pressures. The concept is really simple. As long as you have enough gas pressure that's equal to a column of fluid at whatever depth you're lifting from, you can lift it. It's that simple. So what that means is, early days, you're going to need a lot of pressure. Later times, you don't need that. You can send that booster home after nominally what people are seeing is 2 to 6 months, and then you've got just a normal gas lift system that you're going to operate with. So it's pretty simple, standard setup with the exception of the booster. So the gentleman who's speaking next to you, Bill Elmer, and I were co-authors on a paper. He's sitting right here, and he's going to be speaking next. But we proposed that this was a huge opportunity for the industry. Brandon Pronk with SM Energy at that time said he wanted to try it, and what we needed is someone to try it and show we could really get these high rates. And what this shows is in the purple, 5,200 barrels of liquid a day is the last point of that. So over 5,000 barrels of liquid per day, up 5.5 by 2 7/8. And that was happening at a bottom hole pressure about 2,800 pounds. We were lifting or injecting gas. It never did go up that high, actually, and kicked right off, but we were injecting about 2,000 pounds. This is the original production from this well. And we've we're putting about 1.6 million in that well. So he proved, and it aligned with the nodal analysis approach that we had made on this to estimate how much we could make. It proved that that could be accurate and that we indeed could produce these very high rates up these unconventional wells. So in that pilot test that he did, what he did was he compared it to offset wells they were drilling as part of the same program that were running ESPs. These are different. If you're not familiar with nodal analysis, it's showing the productivity in the IPR curve is the dashed black curve, and then the outflow curve, what's happening in the tubing and the rest of the system, are the colored curves. And the fluid rate is on the bottom, and the y-axis is the bottom hole pressure. So this is showing the bottom hole pressure, and the rate that we produced at. And what you see is the ESP, well, early days on an ESP, what happens? People don't push the rate because they're scared of sand. They're scared they'll fail that ESP early days. And so, in some ways, we can actually exceed that by using high pressure gas lift. And you see they turn it up over time on the ESP, and the rate actually comes up a little bit, goes down, and then it shows a little bit of advantage versus the dashed red line of the high pressure gas lift. But this is 100 days, and the IPR change, the inflow performance relationship, the productivity of the well is changing drastically over those 100 days. And what you see is ESP starts out behind about day 25. If the flow line would have been designed correctly on this, we would have been about the same. They undersized it because I think they didn't believe we could make that much out of it. And there's a little bit of an advantage maybe for the ESP. And then what you also see is what I'm talking about this effect with the gas volume fraction. The ESP gets to where it can't suck it down any lower. Okay, it's struggling. But that's not exactly what's happening with the high pressure gas lift. And so summary is the first 25 days, a little bit of advantage for high pressure gas lift. The next 75 days, probably a little bit of advantage for the ESP, and after that, the advantage to high pressure gas lift. I don't want to talk about this and not this from Bill and I's original paper, and it's just showing that in Eagle Ford terms, we could get down to some pretty low producing bottom hole pressures. Here in Bakken, because the surface pressure is a little bit higher, can't get down quite as low, but still very comparable to what you can get with a pump, either beam pump or ESP. And realizing when I'm saying producing bottom hole pressure, I'm talking about at the heel of the well, right? To get that producing bottom hole pressure, you have to add the surface pressure, whatever you have above your pump, and whatever you have below your pump. Okay, this is just for a typical Bakken well. I'm not going to dwell on this. What it shows is you can make, with enough productivity, over 7,000 barrels of liquid a day. As that reservoir pressure comes down, and so this starts out with 6,000 pound reservoir pressure and then comes down. And as you do, of course, the rate drops down. The amount of gas you need for Bakken wells, because it's bigger casing, you need more lift gas, so 2 to 4 million. You see that there's not much difference between 2 to 4 million when lifting these. And this is, again, trying to be a typical, what in my mind, conservative case, 1,000 GOR with more gas would be easier to lift. So let's talk about costs. Well, the costs of an ESP versus high pressure gas lift, really they turn on what is the failure rate on the ESP. So if you have long ESP run times, you can see that they converge. But I would think any of you that had 20 months run on an ESP would be really happy. Most people are happy with 12 months in unconventionals, and either you're going to have problems sucking it down any lower, or you just get to rates where you just it falls off the curve so much that it just won't run much. And so what this says that if you have high failure frequencies with, it gets to be a significant cost advantage. But I do want to address one thing that I know is a problem here with gas lift, which is compression. And that compression needs to be reliable for gas lift to be the solution of choice. And I know that's been a problem. Bill's going to talk about things coming up next that are really going to help with that, and just some basic engineering solutions that he's applied. I do have a data point from an operator in Bakken that was doing both ESPs and high-pressure gas lift, and what they said was, even with the problems, because they hadn't implemented Bill's solutions, even with the problems they had with the compression, that the runtime was at least as high and usually higher than what the ESPs that they were running were. So, some questions I get asked frequently. What about these boosters? Yeah, I'm not going to give a commercial on that, but I'll say that there are two compressor vendors that operate in the Bakken that do have boosters available. What happens after that booster leaves? Okay, well, at that point, you're in good shape as long as you don't let the well fill with liquids. So what we do is we put a shutdown valve on both the tubing and the casing, and when you lose lift gas, you immediately close those valves to conserve that gas. That actually prevents liquids from coming in and fill the well. It leaves you with a lot of energy to kick your well back off. And we haven't had, I personally thought that was going to be a problem. We haven't had any big problem with that. It's still potentially a problem. So without a packer, won't the gas go into the formation? And the answer is just simply no. Now, actually, Brandon in his well with SM Energy had a pressure transducer downhole, and they confirmed the maximum pressures that they saw were only when they shut the well in, not when they had the well open to flow. If you want to inject gas, you have to shut the well in, right? You can't have another path open for flow. It's going to flow because those gas bubbles, gravity demands, they go up, okay, in that liquid environment. So unless you shut it in, it won't go into the formation. So in summary, the characteristics of unconventional wells make them very amenable to gas lift and the preferred solution in most cases. And lifting them unconventionally has significant advantages, and that's high-pressure gas lift. And we saw that potentially the cost can be significantly lower than ESPs. Thanks.
Larry, thank you very much. Am I queued up here? Okay. Got a couple questions for you, Larry. First of all, have you seen cases where the high-pressure gas lift was not the best lift method for the unconventional wells?
We have a couple of different ones. First, if you have a lot of gas, one evaluation for Permian wells with GORs over 3,000, maybe as high as 10,000 or so. If you have a lot of gas, you become friction limited, and then that extra gas just doesn't help you lower the bottom hole pressure. The other case is actually a Bakken case where they had some wells where they're having great ESP run times, no gas interference because they were very low GOR, very high productivity, and in that case, then actually the ESP looked a little bit better to this operator who does a lot of high-pressure gas lift.
Are there cases where you're going to have to supplement the gas stream, or are you producing enough that you don't need to do that?
Yeah, it's a misconception that you need as much gas to lift the well as that injection rate. The way that system works is all you need is enough gas to fuel your compressor and whatever else draws you have of gas on. And so as long as you produce enough gas, which is nominally for a single well type setup, 100 MCF a day or so, as long as you produce that much gas to fuel those compressors and whatever else you have running off that system, then that's all you need. So you don't need a lot of gas to make it work.
I have seen some recent articles where they're talking about injecting in deviated wells where, say, 45, 50-degree deviation, and your gas is starting to ride up the high side of your conduit, either the tubing or annulus, whatever you're producing up. How do you prevent that in this system?
Yeah, it's a challenge. That's why there's not really any advantage to injecting gas down at the really high angles, because as you change, the flow changes completely. As you go to vertical to horizontal, then sweeping that liquid is a problem. And so, but even though you can't sweep it efficiently at those really high angles, we're running it usually down to 65 degrees or so, and there's some new work that's coming along that I won't talk about that can help you show where the most efficient place to put that gas is. And that brings up another question about, do you need some kind of mixer to mix it? And what we've seen is it's working without that, but maybe it would help. We just don't know. I think there's a lot to learn about what the exact angle you put it in at and what you use to mix it, whether there's a significant advantage there.
And the last question I have is, are you actually stripping liquids from your gas stream prior to re-injection?
No, we're not. No, we're not. And Bill is going to talk about why that is a little bit, but we're not stripping the liquids, and you can put it all down there. The good thing is those liquids, we don't have any gas lift valves that we're going to cut out with those liquids, but that's not necessarily the smartest way to do it. And I'll just any more questions, Bruce?
No.
So if I could, I'd make one comment is there are hundreds of wells that are being lifted with single point high pressure gas lift at this point. What we're finding is the problem is that the people that are doing it mostly are all that we know of are very happy with it. One major shale operator is doing this. They are not willing to share it because they think it's a competitive advantage. We are willing to share it. And so, it's working really well for a lot of people, but we're the only ones that have published on it. Thanks very much.
Thank you. Okay, well, our next speaker will cover the topic of reducing tank vapors by elevating compressor temperatures. Bill Elmer worked for 33 years as a facility engineer and production engineer for Sun Oil Company, Conoco, and EOG Resources before retiring in 2011. He created an R&D company and has authored 11 SPE papers, given numerous artificial lift R&D council presentations, and has received 6 patents in the last 5 years. Please welcome Bill Elmer.
Thank you very much, Bruce.
Thank you.
Test on this mic. Okay, very good. Got this Coke up here because I had some popcorn downstairs and I inhaled it. So if you catch me cough, it's not because I have COVID. All right. All right. I appreciate, again, being here to talk to you guys. I'm pretty passionate about compressors, strange as that sounds. And I've been doing a lot of work on maintaining elevated gas temperatures through the compression process. Has a lot of benefits. The main benefit we're going to talk about today is reducing tank vapors because that's a hot topic. So I will mention some of the other benefits because Larry referred to them. We're going to start out with some physics, right? Everybody wants to start out with physics. Gas gets hot when it's compressed. It's called the adiabatic heat of compression. And I'm hoping this will start the animation. Okay. So when we compress gas, the molecules don't like getting crammed together and they get hot. And when we compress it, right here at the end of the cycle is when we let it out through a discharge check valve. And we let hot gas out of that compressor. Now, we have to cool the gas in order to continue compressing it. Normally, when you compress gas, when you get up to about 300 degrees, any temperatures above that, you risk your lube oil failing on you, and you can have the piston and gall in the cylinder. So we stop compressing the gas when it gets hot. And so to achieve the pressures we need for gas lift, we might have to have typically 3 compression stages. And what happens though, when we cool the gas after each stage, we're overcooling it. And that is causing us some problems. We're creating problems for ourselves by not taking care of, by allowing it to get cooler than it should get. So the next thing we're going to talk about from the mechanical engineering thermodynamics is the phase diagram. And if this thing has a pointer, oh, no, I guess not, backwards. All right. Well, I wish I had. Is there a pointer on this, Bruce? I apologize, I guess not. All right, if you look at the far right-hand side of the curve, the yellow vapor region, there is a pointer right here, sorry. This scale is temperature, minus 200 to about plus 150. And this scale on the left is pressure, 200 to 1400. If your gas is in the yellow zone, that's called the vapor region. It's 100% vapor, no liquid. And that line is the hydrocarbon dew point line. So if you allow the temperatures to fall from 100 down into the 50 range, you're going to be in the two-phase region. That's the blue area. You'll have a mixture of liquid and vapor. If you continue letting it fall in the gray region, it will be 100% liquid. And typically you've got to be minus 100 for that. And that's what happens in the cryogenic gas plants. They cool your produced gas down to below 100 and they knock out all the liquids except for methane, put the methane in the pipeline and make products out of the other stuff. So we need to see what temperatures we need with our gas to stay in the yellow region where we only have vapors present. Because when we condense hydrocarbons in the coolers, those liquids go into the next stage of compression. Now, to protect that compressor from seeing those liquids and damaging the compressor itself, we have a scrubber on the inlet of each stage of compression. We'll remove the liquids and send only a vapor to the next cylinder. So what happens with these liquids that we collect in the scrubber? They go to your tanks, typically. And so they're in those tanks. Remember, these were a vapor when they went in the compressor. They got pressurized and cooled, and they became a liquid, and they go back to an atmospheric tank, which is a much lower pressure than what the gas was when it came to your compressor. They tend to vaporize and create problems for you. So we want to see if our gas, we want to know what the vapor diagram, what the phase diagram looks like for your gas. And we have an easy way of doing that. Anyone here familiar with the Ariel compressor company? I see a couple hands. Yeah, that's a very common industry-accepted compressor. All the rental companies have them. A lot of operators own them. And they have a very easy-to-use design program that's free. And they have paid the Virtual Materials Group out of Houston to put in some some process simulation program in it that will tell us how much of this liquid is going to condense. So just pulling from the website, the Virtual Materials Group provides its clients with proven, validated, and robust thermophysical property prediction packages for the hydrocarbon and petrochemical industry, and they're backed up by extensive data and development support. So we can run this program and we can create the phase diagram. And that's what I did using, the first example is for a gas well in my backyard of East Texas, a Cotton Valley gas well, and it's lean 0.65 gravity. And you see the shape of the teardrop here, and the hydrocarbon dew point curve is right here. And I ran it on a 30-degree day. And what that gave me was how, if you're not familiar with compressors, when we cool the gas, we typically design cooling tubes that will take the gas coming out of that hot cylinder and cool it within 30 degrees of ambient temperature. So if it's 30 degrees outside, the gas is going to come out of that cooler at 60. If it's 100 degrees outside, it's going to come out at 130. And the exception for that is the final cooler, the third cooler. That's designed bigger to really cool the gas down to 15 or 20 degrees of ambient. So on the third stage, if it's 100 degrees outside, you'll have 115. Why? Because when we have a gas well, we want to wring all the water out of it, because we're sending it to a dehy, taking the rest of the water dry so we can put it in a pipeline and send it up to the East Coast to heat homes. We don't want any hydrate issues. So all these compressors that we have up here doing gas lift work were designed to sell gas. And they had really big final coolers on them to get get that gas as cool as possible so the dehydrators would work. All right, so back to this diagram here. You see a stair-step, kind of a stitching here. That's the path that the gas takes through the compressor. In this case, it starts at 80 degrees, the bottom scale, and about 60 pounds, and it gets compressed to 200 pounds and 220 degrees. That's what the program predicts. Then it goes through its cooler back down to 60 degrees. Again, the 60 degrees is the 30-degree approach and the 30-degree ambient temperature. It's inside the two-phase region, so we theoretically should have some of this gas being turned into a liquid if it wasn't lean. And then the next step, we compress it to 400 pounds in the next stage, cool it again, compress it in the third stage to 1,000, cool it again. So that's the phase diagram for this. But since the gas is lean, we don't have any hydrocarbons falling out. And this is an output of the program. And this was a pretty healthy sized compressor, 4993 MCF per day. And it says the only thing that was being condensed was water. We lost 25 MCF a day of water vapor in the first cooler, 4 MCF a day in the second cooler, 2 MCF a day in the final cooler. But we didn't lose any hydrocarbon because the gas was lean. So what if we repeat this exercise with Bakken gas? This is an actual run that I got from JW Power. One of their compressors, they had loaded the gas analysis in it that they got from the operator. And the green curve is actually further out. The one I showed before, you might note that the green curve was about, the farthest it ever got was about 120 degrees. This one, the farthest out the green curve gets is about 145 degrees. So the premise here, I thought, okay, if I put in the program that I'm not going to cool the gas below 145 degrees, I should not have any hydrocarbon condensation because I'm in the 100% vapor region. The blue line is this is the water dew point curve. So looks like I'll have a little water form in the second cooler and the third cooler, but not in the first. So let's see what the program said. And this is another program output. This particular compressor said it would move 888 MCF a day. I've highlighted some of where these values are. And in stage 2, it would have 6 MCF a day condensing. And that's that value right there, 0.006 million. And it would be 99.4% water. In the third stage cooler, you'd have 2 MCF condensing, and it's 99.91% water. But no hydrocarbons were condensing. So this is what we want. If you're putting 888 MCF a day in there, you want all 880 other than water going in your well. So let's say What happens if operator comes by and he opens all the louvers up because he doesn't know that we're intentionally trying to stay at 145 degrees, and now the cooler is dropping all these temperatures. Instead of the right-hand side of the line, they're on the left-hand side in the two-phase region. What would that do? I mean, 75 degrees is pretty easy to do. Like this morning, it was 31 degrees. With a 30-degree ambient approach, we'd be at 61, cooler than this example. But then this afternoon, it might hit 70 out here. It'd be 100 degrees. It's pretty easy for things to get neglected and louvers to not be closed when they need to. So let's see what the run said in that case. This is actual compressor with Bakken gas in it. It says now we're going to have 16 MCF a day condense in the first cooler. That 16 MCF a day is 0.3 something GPM, which is 13 barrels a day. So 16 MCF a day is going to condense into 13 barrels a day and go to your tanks. That's 1.6% of the inlet gas going in that compressor. Stage 2, it's the same story, only worse. We're going to condense 53 MCF a day, turns into 36 barrels of liquid, which is 5.6% of your inlet stream. Total of 49 barrels a day is dumping to your tanks from those two scrubbers. Now, I haven't mentioned about the third stage cooler. There's even more condensation in it, but it's not going to the tanks. And the topic of today's discussion was reducing tank vapors. But if you're running a gas lift operation, you don't want the liquids condensing in the third stage cooler. There's typically no scrubber on the discharge side of the compressor. You just run it to your wells. So you don't want that liquid going into your well and being handled by your gas lift valves. Also, if it gets cool, those liquids will form hydrates once the temperature falls down to about 70 degrees. So you're going to have to inject methanol and things like that. You're probably going to end up in this case having more than 10% of your inlet stream condensing into hydrocarbons. Earlier, I mentioned that if we went in the phase diagram, if we stayed to the far left-hand side, that's what gas plants did. Cryogenic gas plants take it to minus 100, take out all the liquids. Think of these compressors as really poorly performing gas plants. They're stripping your liquid out. You don't want them to do it. You want it to pump it all downhole. But because we're not watching the temperatures, it's condensing a bunch of liquids. So, next page. All right, I wanted to show you what the program said these liquids were going to consist of. It's not just propane, or it's the whole mix. What's coming out of the first stage coolers going into the second stage scrubber? You got methane, ethane, and propane. It's it's about 30%. And the rest of it is gasoline type of components, butanes, pentanes, and then some diesel-y components. Got the whole mix there. The scrubber the third stage inlet scrubber, which is handling the gas coming out of the second stage, even more methane, ethane, and propane. That's about a little over 60%. So when those things get dumped to a stock tank, they want to vaporize. And will they, considering we created 49 barrels a day out of 69 MCF, will you have 69 MCF vaporized in your tank? You could have more, you could have less. It could take some of your crude oil with it. Or it all depends upon the temperature of the crude in your tank. But anyway, that's just to let you know it's what the gas what the hydrocarbon consists of and why you have the tank vapors that you're seeing. That's because it's got a bunch of methane, ethane, and propane in it. Okay, so it's our choice now to control the cooler outlet temperatures. We have to decide, are we going to control them or not? Maintaining cooler outlet temperatures above the hydrocarbon dew point will prevent condensation of your rich hydrocarbons because you're not sending them to the tanks anymore. You don't have any to send to your tanks. And your tank vaporization will not be elevated because they're not present. And if you had I think here in North Dakota, the regulatory body said don't dump compressor scrubbers into your crude oil tanks because it's raising your vapor pressure. Dump them to like a water tank. You may not even have a good way to get rid of them. You may have to haul them off to disposal, these liquids. I don't really know what you do with them if you can't put them in your crude tanks. So anyway, of course, if you maintain cooler outlet temperatures above the hydrocarbon dew point, there's other benefits, such as warm gas injected into well is good for your corrosion chemical program. Corrosion chemicals love 150 to 200 degree range. You won't have any hydrate problems because they form at 70 if you're in the 150 degree range going to your well. And you don't need to inject any methanol, so you're going to save some money on methanol pumps. If you don't control the cooler outlet temperatures, if you just get a run-of-the-mill compressor and you put it out there, you're going to have hydrocarbon condensation in the wintertime unless you're taking methane on that tailgate of a cryogenic plant. You got a pipeline quality gas. And there's not a lot of that going on. Okay, here's a picture of a little one-well gas lift compressor, 75 horsepower. And I put it up there to say, how are gas outlet temperatures normally controlled? Because some of you aren't familiar with this. And here is a handle controlling the louver section. There's not an individual handle for the 3 stages, just one handle for all stages. And there's not an actuator on it to do anything automatic. That's pretty typical, even on larger compressor packages. Now, how do we keep temperatures elevated? Well, there are various automated temperature control systems. I remember first hearing about how Canada used to recycle the hot air coming out of the top back to the inlet of the cooler using, ductwork. JW Power, who's a platinum sponsor here, they're the only compressor company that's affiliated with us that I know of. They are working with my little company to offer several temperature control options. And what we're going to on future ones, typically people use pneumatic actuators that are controlled by Kimray T12s. They're difficult to operate. But what we're going to in the future is I guess I can't get my video to play there. Yeah. Sorry about that. Had a nice video. That thing oh, there it goes. It's shutting now. There's actuators for everything. We don't need to use old technology of a pneumatic actuator that vents to atmosphere. We can do it all electrically now. And so I guess that's about it. There's a lot of other benefits to keeping warm temperatures, and I think maybe if we might have a question about that, I'll follow up. But Bruce, that's the end of my presentation officially.
Okay, well, thank you. Thank you. Are you going to keep me up? The Commission's oil conditioning regulations do require. Maybe it was on me. Sorry about that. The Commission's oil conditioning regulations do require that you keep a vapor pressure of 13.7 or less, and we do prohibit the liquids to be re-injected back or put back into the tank. So according to your first phase diagram, it appeared that if you were staying at above 120 degrees that you wouldn't be sending those butanes back to the tanks. Did I get that right?
Yes, that's exactly right. Go back to that slide. It's a simple premise. The vapor region, if your gas is to the right of the dew point curve, all the molecules will exist in the vapor phase. And in this case, it was 120 degrees. It was about as far as you had to go. With this was just an example that was well illustrated, so I showed it up. But your Bakken gas, it's about 145 degrees.
So you started talking about some of the benefits of the warm gas being injected downhole. Why don't you tell us a little bit more about some of the other advantages of that?
Okay. I think I have got to go back down. I have a slide on that for extra in case. Okay. If we were able to keep the temperatures in the 100% vapor range, on the far right of the curve, all the way to the wellhead, well, your compressor is going to like that. A lot of times if these liquids condense in the cooler, they can form hydrates in the cooler and plug the cooler off. Your gas can't get out of the compressor anymore, shuts down a high discharge pressure. Gets cold in the next 6 hours while a man comes out to start it when it's minus 20 out. It's really, you don't want it. So that's the hot temperatures minimize hydrate formation, not only in your cooler, but in your flow line out discharging from the compressor, in your sales meter run, and in your choke body where you may be using multiple chokes to prorate the gas amongst multiple wells. If you got that warm gas, you don't have to worry about hydrates forming in them. Typically, everybody injects methanol. I mentioned earlier, warm corrosion chemicals work better if you talk to your chemical company. Ask them if that's a true statement. Now, one thing I like, if you've ever been around, I've been around and started a lot of compressors. And when you're running compressors with rich gas, and the gas is condensing in the cooler, and it comes out of the cooler at the bottom, and it runs along your skid, and then the piping turns up and goes in the interstage scrubber. You get that liquid collect in that pipe that's laying horizontal on your skid. A little bit, maybe 1/4 inch, maybe a 1/2 inch. Until it comes time to restart your compressor, and the guy has 10 other compressors to start, and he goes over to the blowdown valve, and he goes, whoosh, and he rips that machine, and a very high rate of gas blows through it and cleans all those lines out, and it sends that condensate that was in the bottom of those lines out through your vent pipe. And as I mentioned earlier about lube oil being rated 350 degrees, lube oil collects with that hydrocarbon condensate. So it's not just pure distillate that's going to evaporate in the air. You've also got it combined with lubricating oil, which doesn't go away. It makes a mess. And you will find most operators know not to park downwind of the compressors when they're going to blow them down. So I like that it doesn't make a mess. Now, if you've got 10% of your compressor throughput vaporizing, you need a 10% bigger compressor to get the gas you want out of it. So that's another advantage. You get more out of your compressors. You're paying for a certain rate, but you're not getting it. And when you put more gas in your well, your performance is better. And it's well known in the gas lift circles that if you have paraffin issues, you won't anymore by putting warm gas in it. Warm gas is a good cure for paraffin issues downhole. And in the Eagle Ford, we actually did some testing with that by elevating the temperatures. We had a problem on every gas lift well with building paraffin on the upper 1,500 foot of pipe, and that's when I was working with EOG. And as soon as we elevated the temperatures to 150, injecting down the annulus in this case, we had no more paraffin issues. So it's good all the way around.
Well, thank you very much.
Thank you.
Again, Bill, thank you. Nice to see the innovative ideas that you've got on high-pressure gas injection.
Thank you. I enjoyed it.
Our last speaker this afternoon is Felipe Ajisafa. Hopefully I didn't chop that up too much. Felipe is an engineer with Liberty Services, and her expertise includes hydraulic fracturing, reservoir simulation, completions, and production engineering in unconventional resources in the U.S. She's also an active member of the Society of Petroleum Engineers with over 10 technical publications in the oil and gas industry. Please help me welcome Felipe.
Hello. Okay, so that's good. Okay. Well, good afternoon, everyone. Thank you for taking the time to be at this talk today. My name is Foluke, just as Larry had introduced me. Okay, I think to use this, the green button will be to progress, and then the back would be backward. Okay, okay. And then this is the pointer. Okay. Okay, we're good. Thanks, Bill, for that introduction. Okay, so today I'm going to be talking to you about a trending topic in the industry now. I'm sure everyone or most people have been aware of it, and it's really well interference, between existing wells that have been in production for a couple of years, and then, you come back later and you drill all these new wells